John Cripps Clark. Tell me about you. You're a science educator, and I'd like to know more about you and how you came to science education.
Well, like many people in educations, I came through teaching, although unlike many of my colleagues, it wasn't a really distinguished career in teaching. So yes, I've been a secondary general science, physics, and to a lesser extent, mathematics and biology teacher. The other thing that I've done is actually to do some scientific research, and that was kind of after I'd finished in the middle of my secondary teaching. I did a Master of Applied Science, which was an empirical study of visibility reducing air pollution in the Latrobe Valley. There are some interesting questions around, as you will, in Australia, we're well experienced with very poor visibility, which is largely due to fuel reduction burning. And it has significant consequences for those people with breathing difficulties, which I've only really just discovered recently. This was done a good 30 years ago, this research. And because Latrobe Valley is the industrial heartland of Victoria and has almost all of its, still has most of its electricity generation from brown coal combustion, there was concern that the reductions, so when you have air pollution, one of the components that's quite important is what you see, and that's primarily due to small particles in the air, below about 10 microns, and those particles reduce how far you can see. So there's also a few other things in the air. Some NOxes can color the air a bit brown in certain urban smog. But so it is important what you see, actually, because it does affect people's health. And there was concern that a significant number of air pollution events where you could see perhaps 20 or 30 kilometres across the valley, and we see those everywhere in Australia, actually, were due to the industrial pollution, either the people with wood burning stoves or fires in the valley, or vehicles, or the power stations themselves. And my study showed conclusively it was actually fuel reduction burning, which was a kind of a bit of a revelation, but never was taken anywhere further. We should have actually done some. We used a special instrument, teleradiometer, to actually measure the level of visibility reducing air pollution, and from there, in a roundabout way, I was primarily looking after children for about 20 years, but towards the end of that, I got a job as a research assistant at Deakin University on a project that I'm still pushing, actually, which was looking at ways of teaching Newtonian mechanics to upper primary students using a lot of practical activities. It turns out that critical idea in understanding Newtonian mechanics is understanding acceleration. And to understand acceleration, you need to understand what speed is. So you need to have a way of students experiencing the measurement of speed. And one of the really nice ways of doing that is to get them to produce graphs of motion. You can produce graphs of motion directly without having to involve numbers, which is kind of an interesting and fairly important idea, especially for students. And once they have graphs and they can interpret those graphs and they can understand motion, they can then produce graphs of acceleration using the same methods that Galileo used of rolling balls down slopes, and the shape of an acceleration graph, which is a rising or falling graph. Can then get them to understand the nature of acceleration. Once they understand the nature of acceleration, you then need to introduce the idea of force. One of the better ways of introducing the idea of force is intimately linked to the representation that you have of force, which is an arrow classically. But one of the ways of getting students to experience force is to get them to measure it. In the same way you got them to measure speed and measure acceleration, in this case by making a force meter, and then you start to relate those two together. So Newton's second law is that really acceleration and force are two sides of the same coin. Whenever we see acceleration, there must be some net force. Whenever there's a net force in an object, it will accelerate. And the proportionality between those two variables is the mass. So getting students to actually do things which get them to understand those basic physical quantities through doing, you can call them experiments, they're not really strictly experiments because they don't have that kind of aim, method, results, conclusion, which we tend to move into in secondary science education. But doing practical activities where they actually start to investigate the world they see around themselves, investigate their experience of the world systematically by taking measurements and then interpreting those measurements. And that interpretation is actually important that they've done that investigation, because that interpretation, they can then feed back to what's happened. So when they are walking across the room and measuring their speed across the room, when they've got a graph up on the wall of that, which is the interpretation, the representation of that, they can then match that back to their experience. When they've got their measurements of the force it takes to close a door or to shift their books across a table or to pull another person, pull a trolley in accelerating motion, they can then match that to what they've seen in the real world. So that kind of idea, which is the idea which is central to the way we think about and we use science. And science is at its heart a relationship between the experience of the real world, and I use the word real advisedly there, and representations we make of that world. And we have a number of, classically with Galileo, it was the mathematization of the real world. So, science really started with physics, with Galileo and Newton, by mathematizing the experience of the world. We also obviously have other ways of doing it: diagrams, graphs, equations. All these ways are representing the experience we have, either directly, more often it's through the instruments, i.e. the kind of broadening of our senses that we have through technologies that we've employed. And again, Galileo was actually crucial here because he took the technologies of lens making, which had been developed in the Low Countries very effectively, and applied it to the telescope, and then used that to then get an experience of, say, the planets being not perfect spheres, and then using that to then reinterpret and produce models, which subsequently, with that and the other measurements that were made by Tycho Brahe and a lot of the other astronomers with Copernicus and Kepler, in really representing it, i.e. as ellipses, as mathematizing it of that world. So that back and forth that we do in science, I think is actually crucial in science education. So with my students who are trying to understand how the world works mechanically, and it's non-intuitive. We live in a high friction world on Earth. So the idea that the natural state of things is moving at a constant speed in a straight line, which is what Newton's first law says, is kind of, it's just bizarre. And you won't get to it just by observing them. You need to interpret that world. So you need to develop the techniques of extracting information from the world, reinterpreting it, and then reapplying it to the world. Once you're aware of that idea, then you can say, I can see what's happening with this car moving along the road, or this ball rolling down the hill, or things. You can then reinterpret it in terms of Newton's laws to understand what you're seeing. But you need this kind of back and forth between observing the world, interpreting, representing it, and then applying that representation back on the world as you see it, to then see, can I predict what will happen when I send a rocket up? Well, you can actually calculate. You can actually calculate Newtonian mechanics. You're probably better to do it with Einsteinian mechanics, which is just a development of Newtonian mechanics. People like to think of it as a great revolution, but it's really just taking things to bigger speeds and bigger distances. So that back and forth that occurs in science is what we need to occur in science teaching. So traditionally we've said, okay, these are the great truths we've extracted from science. Newton's laws of motion, that an object's natural state is moving at a constant speed in a straight line. An object will continue in a straight line unless acted upon in that way, and so forth. Okay, we have ways of stating this, and we deliver that to students. But that's actually, it's to miss the whole point of science. And it's to really misrepresent what science is, because that is only a tool to A, understand what we observe, and B, predict what we will, what we can do with some interventions, what will happen if we do something. And so getting students not, and it really goes to Vygotsky's idea of ideal form. These are ideal forms that we have within science. These are particular bits of in a scientific, using that in both senses of both Vygotsky and in science. This is scientific knowledge which we're giving back to students. We engage them with the need to understand the world that they need. Then we give them these ideal forms which enable them to then act in the world in a way that they couldn't before. It gives them power over the world. So when they can see that condensation on a cold object, the droplets of water you get on the cold object are coming out of the air, they can then understand why when you put a cold object out on a very cold, dry day, you don't get condensation. When it's a hot, muggy day, you get a lot of condensation. They can tell why, because they've then got a model of how the world's working, that there's all these little invisible particles of water that are moving around in the air, and when they hit the cold object, they lose energy, they change state from being a gas to a liquid, and then you start, they accumulate there and you see that droplet of water. They can then understand that it's not the way that many children will, and actually some adults also, will think of this as water moving from inside to outside of the object. You can then start to interpret the world and act in that world. If you want to either collect water, if you're in a desert, or if, or minimize how wet things get when you put them out, you can start to sort of interpret the world in light of this model of the world that you have, which is a model that the world is made of. This is the one that, as Feynman says in his first volume of his Lectures of Physics, this is the single most important idea we have in science, that things are made of these small particles that move around continuously and interact with each other in very interesting ways. And then we can use that to understand the world in a way that we couldn't before. And it's a much more sophisticated, rather than just thinking of this as a Greek idea of Democritus, of things being made of particles, as a kind of a way of a philosophical approach to the world. This is a practical approach to the world. This actually tells you something that you can do something with. So it's not just a nice thing. It's not an aesthetic, using aesthetics in the sense of beauty. It's not just an aesthetic thing. It is largely a practical thing. Now, there are elements of science which are aesthetic. I mean, what you see behind me is really aesthetics. I mean, our investigation of the universe beyond really the solar system really doesn't have any practical use whatsoever. It is purely for the love of knowledge and the beauty of trying to put things together and see things. And a fair degree of mathematics, all the pure mathematics, as G.M. Hardy would say, is purely for aesthetics. So now it turns out that once we start to do that pure mathematics, we find very practical uses of it. So it's kind of a little bit of a misleading thing to try and define that. But the pure and applied idea in science is actually a useful fiction that we bring into play. So yeah, so initially when I moved from a school education into tertiary education, it was through this research project, which I was a research assistant on. Subsequently, I then, as many research assistants do, did a PhD. My children were all fairly young in primary school at the time, and I was doing work in primary schools, running science clubs and working with teachers to do science activities in their classroom. And so I actually became quite interested in primary schools and primary schools as sites of learning science. Primary schools are interesting in that there's a couple of things that happen in primary schools that are quite important. One is that students' attitudes are largely to science are largely laid down in their later primary years. So by the time they're coming into early secondary, they've actually decided what they're going to do when they get to years 11 and 12 in science. They've thought about that already, and their attitudes are largely there. So if you want to intervene in the way that students think about science and the way they feel about it, you've really got to do it at that upper primary level. The second thing in primary schools is that although teachers are uniquely placed to teach good science, there's kind of a self-selection of primary teachers to be teachers who've been unsuccessful in science. If you have been successful in science, you become a secondary teacher. Now, there's a small minority which aren't that way, and that was actually the subject of my research. So they tend to be a bit science phobic. They also tend to be maths phobic as well. But we hammer so heavily the idea that primary schools are there for literacy and numeracy that they tend to pull themselves up by their bootstraps with their numeracy. But science becomes the third thing that you have to do, and the thing that then, if you're at all nervous about it, we've got the sports carnival, we won't be able to do it this term. It becomes an excuse. So thinking about how we get how primary teachers can teach science effectively and how we can induct them into that became quite important. And with my bias towards practical activities, one of the things I really wanted to look at in primary schools was to start to think about how primary teachers can use practical activities in their science classrooms. And for that, and I was actually indebted to Peter Pension, who sat on my colloquium, who pointed this out to me, that I really just needed to look at the very best examples. So I actually sought out for primary teachers who were particularly good at teaching science, and went into their classrooms for a term and just videotaped every science lesson they taught. And yeah, they were all remarkable teachers, all quite different in their ways. Actually, two of them had come in through being interested in science, but two of them had come in with, in fact, almost with a non-science background. But once they'd become teachers, because they were such good teachers, they'd realized how good science was for their students, and it then made a central focus of the way they taught. So they would teach, all of these teachers tended to teach all of their, a significant proportion of the teaching that they needed to do through science lessons. So their literacy, their numeracy would be through science. So it was quite interesting that we had both coming in from the the way secondary teachers tend to come in, which is a love of science, but also half of them coming in from the way primary teachers come in, which is a love of children. And really interesting. So, and since I was a secondary teacher, almost everything I learnt about primary teaching came from those 4 teachers, from basically being in their classrooms for a whole term, and then analysing that. It was a pretty terrible PhD, but it really did get me to have a much more sound understanding of primary science teaching, which then enabled me to then teach that myself without ever being a primary teacher, and teach it quite effectively. The other thing that doctorate did is it introduced me into cultural historical activity theory, and from there to sort of spend more time with Vygotsky over the years and moving into cultural historical theory as well. So it was the kind of introduction there. And one of the things I did while I was a doctoral candidate, amongst other things, was to become fairly heavily involved in student politics. I became president of the Postgraduate Association at Deakin University. I was on the University Council. And that was also part of establishing a reading group in cultural historical and activity theory, which has continued to this day, actually. So it's
John, looking at Australian science education, both primary and secondary, what's the main deficit? What really needs to be fixed in this system?
I think that's the wrong question. I don't. I think, well, if we think about education, it occupies quite an interesting sort of intellectual position, because it's partly a craft and it's partly a science. I mean, a science in the Vygotsky, in the sense that it is sort of rigorous and academic. It never quite does either very well, actually. And to think that there is a single thing or something that we need to do to make it better is, I think, to fall into the trap that conservatives quite often do, that there's just this one thing wrong, that we've got this race theory, or we've got phonics, or we have not phonics, whole language reading. We just have this kind of thing that has to be fixed. Well, it's not. I don't think it's like that in science education. I think I'm, as I told David Kellogg at one stage, I'm an ameliorist. I think we gradually get better, a little bit at a time, and there have been a number of steps in that process for science education. The first was to take the idea of constructivism, which is actually wrong, but it turned out to be a useful monster. And to think, but what it did is got us to think about what students going through in students' heads. And that started the whole misconceptions phase in science education. So we started to think, what are the various misconceptions that students have? And I came a bit after that period in science education, but you will notice that all of the greats in science education, like Russell Tytler, like David Tregest, all started with misconceptions ideas. Now, we've then sort of moved on. We've started to think, well, actually, that's just part of it. That's where they're starting. We've got to think about how we develop students' ideas, how we can actually get them to pay attention to the important aspects of the experiences so that we give students experiences, practical activities, experiments, of the world, or the scientific world they see around themselves. We then ask them to interpret them. Well, we've got to make sure we're directing them to the salient features that are important. We've then got to get them to actually represent, to actually take those salient features and start to make it part of their way of thinking. And the powerful tools we have for thinking scientifically are the models and representations that we have in science. So we induct them into those ways of thinking. And once they have those ways of thinking, those representations in their head, they can then apply them to new examples or to the examples of the world they see around them, to actually make predictions, to understand what they see. So that kind of idea of starting to really tease out what we need to do as teachers to enable that process of induction into scientific thinking to happen is, I think, what we're working on at present in science education research. We're starting to really pull out what it is when you give students an activity to do. How do you direct them to those features which are the important features they need to notice? Now, we've done that sort of unthinkingly in the past. We say, go off and measure how far this ball rolls, or, measure these things. But we haven't actually got them thinking about why they're measuring it or what they're trying to do with that measurement. So direct them to, okay, you're interested in distance, in the way things will move a certain distance in a certain period of time. And so that's why we'll lay out a strip of tape to show that, and we'll put that up, and that will represent in a graph. So we move from that experience, that measurement, to the representation of the graph, to the interpretation of that, to then saying, okay, well, what does that tell you about whether you're getting faster or slower as that happened? So starting to really think carefully about what the teacher does, and rather than falling back into what there is a distinct movement amongst conservatives at the moment towards direct instruction. There is direct instruction there. You do tell students, actually, this is the best way. Once you have this idea of a force being a push or a pull, actually, a good way of representing that is to draw an arrow. So here's an arrow, start using it. And you will find it is a really useful thing to do. It's a scientific concept, or a graph. Okay, you need to understand it and to look at somebody else's graph. Let's talk about some of the scientific conventions we have about the way we represent these things. We start from the bottom left-hand corner, go along, and usually have the time as the horizontal axis. We'll have the distance that's moved as the vertical axis. Okay, that will enable you to look at somebody else's graph. And I've done this with teachers, actually, very experienced teachers who've put the graph up as horizontal lines. And until we then say, okay, somebody else has done it this way. Would it be better if we actually turned that around? And actually, let's reorder them so that you're starting from the left. Now I can look from yours and say, yours actually do say the same thing or say something different. So we start to differentiate between those essential features of the representations of our experiences, which are inherent to the science. They're kind of there, you can't get rid of, and those which are in fact communicative ways we talk about that. So inherent to the idea of force is direction and size. It has, so force is a vector, it has direction and size. How we represent that for convenience, well, we represent it with an arrow. We could represent it in lots of different ways. How do we represent something that is a bigger force or a smaller force? Well, we could make the arrow thicker or thinner. We could put multiple arrows. We've got the convention in science of making it longer or shorter. And that's just an agreement, just to make it easy to move between it. And getting students and teachers to realize this really important difference between things that are fundamental, things that, in the Hegelian sense, I suppose, that are essential, you know, that are the germ of what's going on, and things that are part of our communication that enable us to show that to somebody else and to discuss it and to move back and forwards, and to really start to make that clear, rather than just having something. As you do more science, you get, you know, you get almost by osmosis inducted into this. Well, that's really inefficient. Okay? And we want everybody in society thinking scientifically. So we've got to actually have some way of doing this. And we do it by being explicit, by saying, okay, now we are thinking about how we communicate this to somebody else. Okay, this actually turns out, and you know, you may not know this, but I'm going to tell you this, turns out to be something that's really fundamental to the way that we understand force. We understand that it's this thing called a vector. And this idea of scalars and vectors will actually be really useful, because when we come to energy, or when we come to other, you know, we need to know whether it has direction or just size. And it turns out that almost everything in physics, all the quantities we measure, fall into these two categories. And we discovered this over a long period of time by fiddling around a lot. We're going to tell it to you now, because you don't need to reinvent the wheel here. But actually, we can actually have a rule within our classroom, within our laboratory, that will actually represent it in this particular way. And you know, we will draw graphs this way, or we'll draw diagrams this way. And you'll notice that if you move in various across the various scientific disciplines, not only are there epistemological differences in the way that the different sciences, what they regard as knowledge and how they acquire that knowledge. It's a continuum. It isn't kind of, they're fundamentally different. But you will notice that there are different representational conventions that will sit within that. And so inducting, you know, inducting students into that process and being where I think the great problem of, well, one of the problems that we're working in within science education research at the moment is thinking about ways of enabling teachers to do that in a more precise, a more efficient, a more targeted, a more effective way. And by that, we really start to break it down into the process of the way that we teach science.
Do you teach students about how to communicate science?
Oh yes, I mean, I have actually taught science communication to science students. And one of my little mantras with them was that actually science is not an individual activity. Science is a collective activity. And if you found out something, until you've actually communicated it, it hasn't been found out. It doesn't exist. Gauss invented non-Newtonian, non-Euclidean geometry. But it's not known as Gaussian geometry because he had this kind of obsession with getting things right, because he'd been criticized early on in his career. He never published. So, you know, it's known as Riemann geometry, or I've forgotten the other ones. Even though he actually saw it, he actually thought of it because he was doing something very practical. He'd been hired by the prince to do some land surveying, and because he was probably one of the greatest mathematicians of all time, he then thought about what it meant to be on a plane, or, you know, he thought about Euclid's postulates, and realized that the one about the line and the two parallel lines it was not the same, and you could actually think about things in different. So he actually thought of non-Euclidean geometries. But yes, it wasn't published, so therefore it wasn't part of. So one of the things about science is, in fact, communication is an essential part of science, because science is a collaborative activity. You know, it's built up with people working together and sharing their ideas and building on that in a way that, you know, is actually really special. I mean, there's a sense in which in science, you very rarely go back to papers that were written more than 5 years ago, depending on the discipline that you're in. And you do that because, it's cumulative. We actually do build on what we see before. And therefore, that communication, that talking to each other and thinking of ways that we actually show our ideas is essential part of science.
In explaining this to me, your talk has been littered with references to the history of science right through. What place does the history of science have in teaching primary and secondary kids science?
It's kind of irrelevant to some extent, but it's actually central in another extent. I don't think you have to include history for, to look at science and understand it. But what happens is that, in fact, phylogeny recapitulates the Haeckel's idea that, in fact, the way that you tend to start to learn science tends to recapitulate the way that science developed itself. Now, that's not entirely true. Science has gone off in some very odd directions, which you don't need to go and think. But there's a big effort over in Western Australia to teach primary kids Einsteinian mechanics, relativistic mechanics. But it seems to me, actually, it is worthwhile to develop the way your ideas about motion and force using Galilean ideas, and develop the way that you treat this mathematically using Newton and Leibniz, before you sort of move on to the way that we understand things in a relative sense. You have to actually get to that eventually, but that kind of working through the ways that we came to understand the world actually turns out to be quite an effective way of teaching. And so as a first pass, it's really quite worthwhile to do it that way. Whether, well, actually, it's not whether you teach it, whether you teach it, says this is the science, this is the history of it, is kind of irrelevant, but in fact, it turns out to be a really great way of giving a depth and a kind of a texture to what you do that you wouldn't otherwise, just make it more interesting, exciting.
Yeah, I remember it was only really when I was doing my reading to start university, and I was prescribed Men of Mathematics by E.T. Bell. Absolutely blew my hat off.
Absolutely, exactly the same one for me. Yeah. And I heard a talk from a fairly young, sort of a quarter of our age, mathematician, female mathematician, who was exactly the same. She had become a mathematician through reading that book. And those stories, I mean, I think there's a little bit of a danger here, but there's a big move in science communication at the moment. I think it may be reaching its zenith and declining, hopefully, of saying all our communication is narrative. And I don't think that's true. And I certainly don't think that's true in science. The way we use a graph is not a narrative, it's a visual. And especially now that we have technologies of reproducing and altering visual, it's purely visual communication, but it's also, it's never purely, it's always visual linguistic. The way that we have of doing that will actually change the way that we think about that. So we won't have just that kind of linguistic, we'll have other ways. But it's still a very powerful way, that story. And let's face it, the narratives of how things came into existence, of why we developed our ideas of thermodynamics. Thermodynamics is very poorly understood. And actually, it does help to think about this is something that came out of the Industrial Revolution. It came out of the need to understand heat and how we could use heat to actually get work. So the idea of heat being used, from cold and being used to do work was actually very powerful, but it then generated those scientific ideas. And then you can start to understand what we mean by the first and second law of thermodynamics in terms of not just the logical connection between the way heat moves and the relationship of heat to disorder, to the various different possible states of a system, or energy transfer to that, but also in terms of the way the problems that people were trying to solve at the time. Boltzmann and Carnot and Kelvin and Joule. Joule was actually sitting in his, one of the, he was the son of a brewer, very successful brewer, and was in Salford, sitting in the basement. I don't know whether it was the basement, but anyway, he had a lab setting up in the family home, dropping weights with little paddle wheels in insulated jars and measuring the temperature. And the real critical factor in the success of that experiment, and the reason it was not taken very seriously at the start, but was in about 10, 15 years later, was the improvement in the measurement techniques. The fact that they then got thermometers were actually accurate to 0.1 of a degree, whereas previously it had been accurate to about 1 degree. And the changes in when you mix up water, you actually do this with a bottle. You can actually shake a bottle and stick a thermometer in, and you will notice it will go up by a degree or so. Feynman actually talks about one of his talks, and I directed students to look at that talk, and one of the students went off and did that experiment and noticed it. So you can actually shake a bottle. In fact, it turns out it's better to shake a liquid other than water because of the heat capacity of water. So you need to put a lot of energy to change the temperature of water by a small amount. But if you use alcohol, you can actually shake it and get it to go up 2 or 3 degrees without too much trouble. So the idea of what we're trying to do and the ideas of in the science, I think there is a kind of recapitulation in the way that we learn it, but there's also a kind of enrichment that we get by thinking about the history, and also this, the sociology of science, the way that we've worked in science, because that actually tells us about the way we need to work in science, the way it is a communal activity, the way that it builds from each other.
John, watching you and listening to you over the past couple of years since I've been attending your reading groups, I've noticed that you do have a pretty close interest in the Australian Indigenous people. What could you tell us about Indigenous education in relation to science?
I'm going to, and you may want to edit this out, I'm going to say something that's actually controversial in this respect. I really think science started in the 14th and 15th century in Western Europe. And that there is actually no such thing as Greek science or Indigenous science. It's a very particular and peculiar form of knowledge, and it has arisen in a particular culture, a particular time, and that contingency has caused the kind of things that we see in science. It's a white male Western thing, because it came out of that society, and we will change that. But it's important to realise that's where it started. And I think it is misleading to talk about Indigenous science in the way that we tend to do that, because I think it really is Indigenous knowledge, and we need to think that there are various knowledge systems. And we knew a lot about the world before we started to work scientifically in the 14th, 15th century, through various ways. And in fact, all groups and peoples know a hell of a lot about the world, but it's not necessarily knowledge that's acquired scientifically. Scientific way of working is very particular. It is knowledge, it is important knowledge. It actually matches up with scientific knowledge as well in powerful ways. And we see, things that we, find out in science that is already known through either remedies or whatever, things that are not known. But it's a body of knowledge, and I think we demean it to some extent to think of it as, you know, it's this word social science. When we say social science, we're trying to give epistemologies and which are perfectly valid and powerful in their own area, a patina of the success of science. It's, you know, science has been unreasonably successful, and by saying, oh, it's indigenous science, we're trying to say, oh, well, it's really actually much better than, you know, just indigenous knowledge, because it's got this word science attached to it. It's a body of knowledge. It's a powerful body of knowledge. It has consistency and epistemology of its own. And to say it's kind of indigenous science, I think, is to misrepresent what's going on.
I'm certainly not going to edit that out, John. I completely agree. And I think there have been recent controversies which have highlighted the importance of not putting an equal sign between different cultural ways of life and ways of knowledge. And putting the equal sign actually obscures and demeans other forms of knowledge apart from specific practices such as science. But it also raises the question about communication, because you pointed out how central science communication is to science itself. So the question of communicating science ideas, not just to a novice, but perhaps to an adult who may be a very worldly, very knowledgeable adult who is not a science person. How do you talk science? How does science share and learn from indigenous knowledge in a productive and fruitful and respectful way?
I suspect it's something that we're still working out. I don't know if there's kind of a simple magic solution. One of the bits of recent pieces of science which has influenced me a great deal, and I've forgotten the researcher at Melbourne University. It was looking at land use in a small area in northern Tasmania. It's adjacent to the Tarkine, so it's an area that at present is mixed agricultural and forestry use, and has in the gullies regrowth of rainforest, of temperate rainforest areas. And one of the nice things that his team went back is they went back and did a pollen analysis, but they also went back and looked at the accounts of the first Europeans who arrived in northern Tasmania of the landscape. At present, the landscape it's rainforest actually, but when Europeans first got there, it was actually open grassland. And so they did careful analysis of the pollen in the soils, doing stratigraphic layers down there, and looked at the history and what's happened, and showed, yes, conclusively that in indigenous times that had actually been open grassland. Since the indigenous people had been removed and the burning systems they had stopped, it had reverted to being rainforest. There's a couple of really nice messages about this. One is that all landscapes in the world, and especially in Australia, except for Antarctica, are human-created landscapes. There's no such thing as wilderness. It really, very top of mountains, perhaps Antarctica, there's a few odd places, but most of the places we live are actually human created. And when we think of, the natural state of Australia or anywhere, it's kind of, you have to think of it in terms of with human intervention. But the second thing is the way that this is actually a kind of a putting together of various bits of knowledge. It wasn't just, that paleobotanical analysis of the soil samples in an area. It was looking back to the historical. It was taking knowledge from indigenous. There's a little bit of some stories, even though it's been hugely disrupted in Tasmania, of that kind of knowledge. Much better when you get to northern Australia, where you've got kind of a continuous line. To really develop what is a scientific idea about the way that the landscape has changed over the years, and the influences, the biological influences of fire and natural regeneration. The idea that we've had developed over the last about 20 years that rainforest is essentially areas that aren't burnt, and as soon as you stop burning, you'll get the rainforest moving back. It's a really great example of that. We have a few examples in northern New South Wales, southern Queensland as well. In fact, right up through Queensland. So I think there is, when we start to do scientific research, it becomes meaningful when we start to connect it out to other forms of knowledge and to build the story, the narrative, the explanation of the world that we see it in terms of a number of interacting knowledges. One of those powerful ways that, especially when we're talking about landscapes which are still owned by and dominated by Indigenous peoples, unless we're including those knowledges in the way that we think about that we're going to get it wrong. In the same way that when we do a lot of scientific, well, it's not really a great example, but I'll use it anyway. When we think about climate change, the science has been impeccable. It's been just always there, but because we've failed to take into account ideas from sociology, from science communication, we've failed to actually make the use of that knowledge that we should. In the same way that if we go out and catalogue animals, or do scientific studies of animals in the desert regions, unless we take into account the other forms of knowledge there, and the other big form of knowledge is the Indigenous knowledge, and build that into the way that we use the scientific knowledge, then we're going to be wasting our time. So I think it's through the integration of these various forms of knowledge and to give them their status as separate epistemologies, and not to try and shoehorn them all into being the one thing. And there will be competition. There will be points at which I will say that actually the Indigenous way of understanding this is more important than the scientific way. For a science point of view, doing this will make no difference whatsoever, but the Indigenous people have a belief, and I think that I'm going to go for that. And the same, the same applies in lots of other areas, that we don't, science is incredibly powerful as a form of knowledge, but it's not the only form of knowledge. And when we do things in the world, we use other forms of knowledge. If we ignore the science, and that applies in mining land across Australia, if we ignore the science, we're going to get ourselves into terrible problems. But if we ignore other forms of knowledge, we equally get ourselves into terrible problems. So it's really important to start to think of these as valid pieces of knowledge, which have an epistemology and have ways of maintaining quality in them as well. And we work in this in science, all different. There's a huge debate about reproducibility in science at the moment, and the ways, we've had these classic studies where we've gone and redone 100 of the most important psychological studies and found that we've only got 20 to 30% of them right, which is thought to be sort of shocking, but it actually turns out to be quite interesting. And what we do with peer review and the way that we think about peer review, because we've now got lots of rubbish coming on, and we need to think a little bit more, and we want to get things moving more quickly with, pre-publication with COVID. So we're starting, we're continually revising the way we think about how we maintain quality, and how good our science is and how useful it is. The same applies to other forms of knowledge. If we think of it, Indigenous knowledge, then it has its own epistemology. It has its ways of maintaining quality, and that will need to be worked on. Now, it's not my job to work on it, but we need to give power to those people working and developing and building up those bodies of knowledge and documenting them to actually do that and to think about that.